Hello everyone, I'm Tao Zhong, a contributor to isula. I'm honored to share isula with you today. After listening to the three speakers, I think we all have a basic understanding of sandbox technology and Quasar. Now I'm going to talk about isula, a lightweight container engine that's closely related to sandbox technology and container runtime. Container engines are used to create and manage containers at the operating system level. They can bundle applications and their dependencies into a proto-container, allowing them to run in different environments. Container engines usually use sandbox to isolate process and file systems within containers. So even if an application in a container is checked, it won't affect other containers or the host system. I will divide my sharing in 4 parts. Let's start with the first part. You might be thinking, why openEuler purpose with isula when Docker is so popular? Well, let's check out the CISDIC 2022 container usage report. As companies falling on board with containerization, the number and the size of containers being used in growing rapidly. The recent report showed that 5% of businesses are already using 5,000 or more containers. The number of containers per host has also increased by 24%, going from 14.6 to 15.7, and the maximum number of nodes has reached 2015. This can be a problem in environments where resources are limited or when deploying higher density container nodes, as the amount of resource containers consumed can be overwhelming. Additionally, container concurrency speed is one of the bottlenecks in large-scale deployment. This is why we are development a fast and light container engine, isula. Isula got its name from the bottleneck ant in South America. Even though it's tiny, it packs a punch. Getting struck by one feels like getting shot with a bullet. It is one of the most powerful insects in the world. Isula is the foundation of the Isula system, offering adaptable, dependable, and safe support for all kinds of situations. It resumes small memory and has higher energy, just like its namesake. Let's learn more about isula. isula is a super lightweight container engine implemented by C and C++. It is known for being fast, flexible, and is not limited by hardware specs or architecture. And isula supports the standard OCI interface and can easily integrate with other OCI runtime like Runc, Kata, and Quasar, making it compatible with the container ecosystem. Due to its lower resource usage, isula is suitable for scenarios that require relatively higher resource restrictions on container engine usage, such as city, embedded, edge side, and so on. isula can run different types of containers, such as common containers, system containers, and security containers. Common containers are the usual ones that people use, like Linux containers. System containers are like common containers, but they can manage systemd service while running. They share the same kernel and the host machine, but only isolate some fields and proc, so they are not the same as a virtual machine. System containers are great for scenarios where you need to run source-intensive applications and move your business to the cloud. Secure containers are a mix of virtualization and container technology. They provide stronger isolation between containers by using a virtualization layers. So each secure container has its own kernel and lightweight virtual machine environment. This means the different security containers running on the same host machine won't affect each other. In the second part, Let's take a look at the architecture of isula. On the diagram, you can see that isula has a command line interface that's similar to Docker, which you can use to manage containers. It also has a gRPC API that follows the container runtime interface standard. It implements the CRI gRPC service, which includes the runtime service and the image service. This gRPC service listens to the local unique socket, while kubelet runs as a gRPC client. As a demo, isula takes care of container lifecycle management, including image storage and transmission, container execution and monitoring, resource management, and networking. To make it easy to understand, we divided isula into 4 different modules and grouped them into 4 main service execute. You can see in the ground. The image service handles image management tasks like downloading, querying, and deleting image. The container service is responsible for container-related operations like creating, storing, and deleting. The network submodule takes care of managing the network of CRI ports. When a port starts, it's added to the network plan specified in the configuration file using CNI. When it stops, it's removed from the network plan, and the relevant network resources are cleaned up. Finally, volume service provides local volume management. The implementation of service relies on the 8 modules shown in the diagram. Ultimately running process in container runtime. The container runtime implementation relies on system core, specifically the namespace and the C group features of Linux. Overall, the structure of isula is very clear, with each layer's function being well done. Next, let's analyze the difference between isula and Docker from the core chain. When Docker runs a container, it goes through a sequence of steps involving Docker, container shim, and then the container runtime. But isula starts the container through isula shim or LCL, and then through the container runtime. Also, to make things easy for users, isula supports the conversion of Docker local storage and even allows for the porting of Docker containers to isula. In general, isula has a simpler and shorter core chain compared to Docker. This means that isula consumes less memory and has faster concurrent performance than Docker. In the third part, let's take a look at the performance comparison between isula and Docker. The first comparison is to start 2 identical RunC containers on the same machine using isula and Docker respectively. When we can see that the memory usage of Docker process is more than twice that of isula, and the memory usage of container shim is more than 6 times that of isula shim. The experiments clearly demonstrate that the isula consumes fewer resources compared to Docker, which can solve the problem of higher resource utilization of container infrastructure that we initially proposed. In addition to the memory advantage, let's take a look at the performance of isula and Docker in concurrent create, startup, stop, and the deletion of containers on the same machine. From the graph, we can clearly see that isula and RunC outperforms Docker and RunC in all 4 scenarios, and that isula and LCR is also outperforms isula and RunC in all 4 scenarios. The data provides that isula is far supervisor to Docker in concurrent performance can break through the bottleneck of container concurrency speed. In the last part, we will use two simple demos to show how to use isula for container operation. The first demo demonstrates the command parameters provided by isula. This picture shows the main commands that instructions of isula, covering most of the commonly used application scenarios. These contain the operation interface of the container, such as create, start, stop, and delete. It also includes image-related operations such as download. Next, I will demonstrate how to use the isula command line. Wait a moment. You can see we can use pull command to pull the image we used to create container. In this demo, I pulled BusyBox and Ubuntu image. And if you want to create a container, you can use first you can use create command to create a BusyBox container. And you can see the state of container is created. And then you can start it. You can see the state become up. Or you can directly use run command to run a container. Use this method, you can quickly see that the state become up. And if you want to pass the container process, you can use pass command. And if you want to restore it, you can use unpass command to restore the container. And finally, you can use the stop command to stop the container and set the time to 0 to short the time to stop container. And also you can use rm command to delete the container. The second demo is to create a container in Kubernetes cluster deployed by isula. You can see this is a YAML file. This is a container that run a date command in a loop, and we set the resource limiter. We limit the memory to 200 megabyte, and we can use apply command to create this sandbox. We can see that pod state becomes running, and we also can see that the parts container and the application container in isula. Next, let we use exec command to verify the resource limit we set in configuration. You can see that the value is the same as the configuration, and we also can use logs command to show the containers log. Finally, we can delete the container, use delete command. Through this demo, you can see isula can be well integrated with Kubernetes. In short, isula is an excellent container technology that outperforms Docker in memory consumption and can break through the bottleneck of container concurrency speed. It also provides rich commands and is suitable for various application scenarios. I hope today's sharing can help you better understand isula. Thank you all.